Alright, so I'm going to tell you about some of the stuff we've been up to at Queen Mary and with our collaborators and other places. That uses DiRAC resources and other HPC resources in the ecosystem. And some of the reasons we had to go to some of these different things because of what these different resources offer. The motivation of the setting for this is that we're studying plant formation. And we're dealing in a new modern context of plant formation. We're starting to understand new things about protoplanetary disks. The big thing here is that these disks, we now know from the structure that arises from the non-ideal MHD of them, is largely laminar, because for the most part these things are unionized. So here's a cross-section of the disk around the central star, and only in the center regions is it well enough ionized to have something resembling ideal MHD going on. Through most of the disk, strong non-ideal effects lead to a quenching of the maybe a rotational instability, which you may have heard of, or generally the coupling between the fluid and gas. And so it ends up in a pretty laminar or low turbulent state. So it's then a wind-driven disk as opposed to a viscous accretion disk. So this is just sort of a background thing. What we need to get into is really the computational requirements of dealing with this situation. Although I will just show you here one example, numerical model of this disk from a paper we wrote a few years ago. And this gives you an idea of what this laminar structure is. These black arrows are the velocity of the gas, and you can see it's coming off the surface here in a high velocity wind that's carrying angular momentum away down to the disk midplane. You're not seeing any black arrows that are showing up much at all. The velocity of the gas flow is quite laminar in here, and the magnetic field geometry that's shown by these white arrows and the color of this color map in here is quite smooth and tame because of these large non-ideal effects. Planets then forming out of these protoplanetary disks are going to interact with it. And when you drop a planet into a disk, there's a two-dimensional simulation. This is a vertically integrated set of equations. Where I drop the planet in, and you see here it has an effect on the disk gas surface density. That's due to the gravitational interaction of the planet with the disk gas. You see a couple of features. There's an inner spiral wave here. There's an overdensity that tugs on the planet, increases its angular momentum, and tries to make the planet migrate outwards to the disk. There's also an outer spiral wave here behind the planet. That overdensity tugs on the planet and drives the planet inward. And it's a little bit harder to see as a direct feature here, but there's also material in the coorbital region, which is catching up with the planet from behind, undergoing angular momentum exchange, and then ending up on the outside of the planet's orbit, and then a matching stream on the other side, doing the same thing from outside to inside, with an angular momentum exchange. Any mismatch between these angular momentum exchanges, like the ones with the two spiral arms, would cause the planet to have a net movement inwards or outwards. So when we try and understand the formation of planetary systems, in particular why this interaction wouldn't just drag all the planets right down into the central star, we need to understand the fluid dynamics of what's happening in this disk. So, as an attempt to organize what's already known about this, I put up this map here. And in the days when we thought we had viscous accretion disks, we were in a pretty simple situation where there was a reasonable analytical approximation and simple two-dimensional numerical models which could describe these type 1 and type 2 regimes of disk-planet interaction from low mass to high mass. Over here, once we go to these low viscosity disks, we're in a situation where we get this much more complicated set of phenomena with various things that give transitions between those based on changes in the physical parameters. So where our research is sitting over here in this rose-tinted side at low viscosity, where we have this complicated set of things going on due to the fact that it's a very low viscosity disk. So I'm going to show you this movie here of one particular, of down here in the low mass end of the parameter space, and to highlight the importance of the vorticity of the flow, which is a way of labeling, you can think of it as a way of labeling the specific angular momentum of the gas fluid elements that are interacting with the planet. I'm going to show you two things. One disk with which is quite viscous, so this is the traditional old way of thinking about disks, and one disk where it's an inviscid disk, and I will drive the fluid in with what I'm calling here a laminar magnetic inflow, but it's just a torque that makes the disk on large scales do the same thing as it does in the viscous disk. And you can see here that the planet migration trajectory as it goes in is very different in these two cases, and in the end it's due to this co-rotation torque from these things, this stuff that is catching up with the planet and then getting past the outside on each side, which is arising differently in this laminar disk from the viscous one. So I show you here, start the planets out. They're now both in inviscid disks, and we're getting this pile up of vorticity. And then when I turn on the viscosity or the magnetic inflow, very different things happen. Over here, the viscosity diffuses momentum around. It keeps the vorticity in a nice gradient. So you get a very well-defined, a constant and well-defined asymmetry between these two exchanges of angular momentum due to the gradient in the flow across there. In the case where we have low viscosity, the interaction, the memory of the system, the ability of the material to hold on to one vorticity leads to this strong asymmetry and a very different net torque on the planet, and that planet goes rushing outwards instead of continuing inwards. Right. There's other things that happen here beyond just the local dynamical effects in the flow. Because of, when we're at low viscosity, because the disk does not smooth itself out anymore, once I put a planet of a mass high enough to actually modify the surface density in, instead of getting a smooth, constant motion inwards due to base pretty steady structure, density structure around the planet and the disk, the planet, as it modifies the disk surface density, the modifications it make will undergo secondary instabilities and form these vortices. And you can see here these C-shaped things flashing around. And so there's a thing called the Rossby wave instability, which is also what gives you things like, which is also a thing that is dominant in weather systems on the Earth with the jet streams. And here it's kicking off, and it will bounce the planet around and slow it down while it's migrating in. And we then get into a situation where we need very high numerical resolution to actually talk about these, to study this, because these instabilities in vortex formation change as you go to higher and higher resolution, of course, because you don't have a viscosity smoothing the flow anymore. So, as a contrast of two different situations, here is a situation, again, with a planet of a mass such that it's modifying the disk surface density, and it's able to slow down its own inward migration. The time is still ticking by up here on the top here, the later part of that movie. And you can see what that is. It's because the overdensity from and the torque from the inner spiral arm and the outer spiral arm are being modified by the planet itself as it's changing the gas surface density, as it's building this partial gap and these density bumps to the front, to the inside and outside of the planet's location. And with a bit of viscosity, you get a situation where the planet slows down a reasonable bit and makes this nice steady state. There's a classical, or maybe not classical, maybe I'm just saying classical because of my age. There's an older prediction that in this situation in the inviscid disk, this feedback, this fact that the planet modifies the disk surface density, will result in the planet actually stopping its migration. Here, with sufficient resolution, we can find that we can get a converged solution with some viscosity, and the planet, well, it slows down, it doesn't stop, but there is at least a smooth modified migration that goes on there. Now, this is at some a situation with some level of viscosity, and this inertial limit should kick in really at zero viscosity. Now, however, when we crank up the resolution here to a resolution which is actually a little bit silly for a purely two-dimensional model, because I have a disk system, a thin layer of gas. I vertically integrated it, but now I'm describing the horizontal direction with 93 cell for each thickness of the disk. I'm describing the horizontal direction with 93 resolution elements, and the vertical way I've just integrated that in. So I'm treating now something as two-dimensional that at the small scale definitely isn't. And I can get a situation where, again, this Rossby wave instability kicks off all these vortices you can see here. And this wildly modifies the feedback slowing behavior of the planet. Instead of stopping, these vortices are able to liberate the planet, bounce it around, and keep it moving inwards. So as we went to go to high resolution in 2 dimensions, we find that the one-dimensional calculations which are done, and various papers, a number of papers have been written using that as a prediction that the planet should stop. That stopping just doesn't happen because there's two-dimensional effects that you cannot see in a one-dimensional analytical model. The next problem you have here is that, well, you get that vortices should show up and mess around with the planet, but as you increase the resolution, the numerical viscosity goes down, so you get more vortices, so you get changing behavior, at least in 2D as you go down. These different curves here are actually resolution doublements, with this red one being highest. So, right, I mentioned this thing, I'm going to slightly ridiculous resolution for 2D. I'm also getting to the limit of what I can do on about a tier 2 computing facility. To do something, clearly there's something that has to happen in these problems in 3D, but I need to go to a bigger machine. And so this is where we kind of come into a bit about the situation of being in the UK that probably need to be doing more talking about, I think. We're on DiRAC with these tier 2 systems. There is nothing in the UK that's a tier 0 system. I'm a little bit shaky on exactly if Archer counts as a tier 1 at the moment. But the other thing is SDFC funded research, this isn't stuff we can do on EPSRC systems. So we are forced to go to Prace to get tier 0 access. That also means that instead of going from a few, we can't go to say 10 million CPU hours in a year, we have to go to at least kind of 20 at this point in order to qualify for access to those systems. And we need pretty serious scaling to get on there. So it's a bit of a jump in thinking about codes and how you manage things to do this. Right. So we've done some of that. I can show you some of the results from our 24 million CPU hour campaign of simulations. So these are low mass planets. This is a 2D model, the sort of thing you can run every day on your tier 2 systems, and this is a 3D model. And see here is the migration trajectory of that planet from the 2D models and the 3D models. And you see that in 2D, what happens is we get this slowing down of migration. That happens again from one of these effects I was mentioning earlier, the vortensity memory in the co-rotation region. That planet that was doing the crazy turning around and going in thing. You see up here in this map of vortensity, this is around the disk this way, and this is in the disk towards the top of the page, so the planet is on the edge here. So this is stuff that is co-orbiting with the planet, it's having an encounter with the planet and getting jumped to the inside and outside. You see that the color of this sort of retains the initial color and vortensity of the material where the planet started as it's moving in to the disk. And so that's giving rise to this slowing down of migration. That's giving it a positive rotation point. Whereas in 3 dimensions, something very different is happening. You see all these new structures with vortices. They don't build up and grow as bigger and bigger things as vortices do in 2D. These ones break down. And there's these diagonal striations showing up in the flow. The thing that gives rise to this behavior, where it continues in, and that's actually speeding up a little bit, is due to this bright color that's showing up in the vortensity here, in the corotation region of the planet, which is the opposite of the dark color, which shows up here. So there's a new effect that shows up in 3D once you're able to run these simulations at enough scale. And indeed, it turns out that this is inherently just a property of the 3-dimensional disk versus the 2-dimensional disk. So these are both where I've stopped the planet moving, so you don't get this kind of teardrop shape into the material that's trapped anymore. You see here that this enhancement of the vortensity, the fact that it gets towards brighter colors, this one stays at the background average, is inherently just about this 3-dimensional movements of the gas. Okay. So I shall jump down to the end here. So, this is the situation. We understand that there's these low turbulent inviscid disks. There's this new non-linearity that comes up in the planet-disk interactions. And because of this, because of these small-scale features of the flow, we need to use much higher resolution simulations than we did before to understand this phenomenon. There's a bunch of papers if you really care about reading those things. Thank you.
Do we have any questions for Colin? Yes.
Yeah. So the shift between the 2D and 3D behavior is very interesting for many reasons. But one question I wondered was, you're seeing essentially vortices that persist in 2D being destroyed in 3D. Do I understand that right? Or?
Well, I think that's a property of 2D versus 3D flow. Vortensity is exactly conserved in 2-dimensional flow.
Yeah, one thing I wondered about is we've seen a lot of work trying to explain things like asymmetry disks that invoke large-scale vortices, viscous traps, and that kind of thing. And most of these are based on 2D simulations. Is the implication there that these people, these simulations really?
I'm not making a claim about that.
No, but
that is actually quite interesting, and there's a good reason to get more big machines to do these calculations right. Because what I see, actually, you can see in that movie. I guess that isn't on the web or anything, so I'll just go back to it. For this movie, you can actually see small vortices here grow into a big vortex. See that small stuff? And then it becomes this big blob that's going by. So in 2D, you definitely get a buildup of small RWI modes to like high-end modes to low-end modes. So that's suspicious, yeah.
Any other questions for Colin? I have one about the viscosity. So the problem that you have is that as you increase the resolution, nothing but viscosity drops.
Well, that's a good thing.
Right? Which is a good thing and a bad thing, right?
Yeah.
Because it means that your things never converge.
Yeah. Well, okay, there are things that converge. So this is, I've had to use a couple of times. I've cheekily used the word aisles once in a while, an implicit large eddy simulation. And once in a while, particularly in, say, compressible turbulence, some star formation things, and some other issues like stream instability. That's a bit of a plan formation thing. You can get a scale-wise convergence where once there's something happening at the small scale, things work out at the large scale. That's because we don't have a good subgrid model. We don't actually have a well-motivated LES model for this kind of turbulence. That's in most of the astrofluids I know of. That's one of the main ways that people feel with variable viscosity flows and the temperature to do that. There's been a couple of